So this is a video of me going over perpendicular lines with respect to parallel lines, and this is Unit 1, Section 7. So I'm going to go over this review for you guys just to prep you. This first one says, name the theorem that justifies the locations of the angles 5 and 6. So we're talking about this angle and this angle. Those are a linear pair. And we know they're supplementary. Next one is 2 and 8. So we're talking about this angle down here and this angle up here. These are alternate exterior, my bad. Angles. And these are congruent. Then we got 4 and 5. This one here and this one here, and they're on the same side of the transversal and inside the parallel line. So these are same side interior. And if you notice, they're not the same shape, so they would have to be supplementary. The next one's 5 and 3. 5 and 3. These are alternate interior angles because they are on alternate sides of the transversal and inside the parallel lines. And again, you can tell these are both obtuse, so they're going to be congruent. Then we've got 8 and 4. 8 is here, 4 is here. These are corresponding angles. And again, these are the same shape. They're both acute angles, so they're going to be congruent. 5 and 7 are here. 5 and 7. And this even looks like what they are. They're vertical angles. And these again are congruent. They're both obtuse angles. This next problem says, name the theorem that justifies solving for x, then solve for x. So to solve for x, I'm going to use this relationship right here, and this relationship is they are a linear pair. So the way I'm going to do that is add them together and set them equal to 180. When I do that, I get 6x plus 30 equals 180. So 6x equals 150. So x equals 25. Then we could use one of two relationships. Let's go ahead and plug this 25 back up in here. So this one is going to be 2 times 25. That's 50 degrees. And then this one over here, the one on the right, 4 times 25 is 100. So this is going to be 130. So we could use the fact that these are equal here because they are vertical angles. So if we do that, then we would say 6y minus 8 equals 130. So 6y equals 138. So y equals 23. There's obviously another relationship that we could use here. We could use this relationship, the linear pair angle. So we could also use the linear pair. And to do that, we would do 50 plus 6y minus 8 equals 180. 50 minus 8, 6y, that would be plus 42. And then we subtract the 42 from the 180, so that would be 6y is equal to 138 again. So either way, y is equal to 23. So again, remember, you're always going to have to justify your answer. This next one is a proof, and in this proof it tells us that P is congruent with parallel with R, and that 1 is congruent with 3. So P is congruent to or parallel to R, that's given, and so is 3. And those are the first two things I would always do. I would look for these two pieces of information in my proof, and then I would put givens next to them. If you look in the drawing, 1 is congruent to 2 because they are corresponding angles. And then look here at step 2 and step 3. Notice we've got 1 is congruent to 2, 1 is congruent to 3. This one drops out and we're left with 2 is congruent to 3. Anytime we have 3 angles like that, we're going to use the transitive property of congruence. And then anytime we are looking to say that lines are parallel, we're going to use a converse. And we now want to look at 2 and 3. And if you look at 2 and 3 here, 2 and 3, those are alternate exterior angles. So this is going to be the converse of the alternate exterior angles theorem. And again, I want to emphasize to you that when we're looking for proving that lines are parallel, it's always going to be a converse. So today we're going to prove and apply the theorems about perpendicular lines. And so the perpendicular bisector of a segment is a line perpendicular to a segment at the segment's midpoint. I want to point something out to you. This symbol right here is the perpendicular symbol. So in case you don't know what that is, that's what this is, the symbol that shows us that two lines are perpendicular. And perpendicular means that the lines have right angles where they intersect. The shortest segment from a point to a line is perpendicular to that line. This fact is used to define the distance from a point to a line as the length of the perpendicular segment from the point to the line. Let's see what that means. So here it says, name the shortest segment from point A to BC. So here's our point A, and we're trying to find the shortest distance from it to BC. Well, we just read that that's always going to be a perpendicular. So this is our perpendicular right here, line. That is from point A to line BC. So that AP is going to be the segment that is the shortest distance from point A to line BC. Then it says write and solve an inequality for A. Here we're going to say AC. AC is always going to be bigger than AP because AP is the shortest segment. So then we're just substituting in the values. 8 minus x is greater than 12. We're going to add that 8 to both sides, and so our answer is x has got to be greater than 20 for this to be an actual shape. Okay, so on this one, go ahead and do this and then come back and check with me. Name the shortest segment from point A to BC. So again, we got our A out here and our segment BC. So the shortest distance, again, is going to be this perpendicular line right there. That's going to be our shortest distance. So that's going to be AB. And then we're going to write and solve an inequality again for x. So this time we know that AB is going to be smaller than AC, or we could say AC is greater than AB. Doesn't really matter which way you do it. So that would be then 12 is greater than x minus 5. We're then going to add the 5 to both sides. And this time we're going to say that x must be greater than 17. Because again, we know that this length, AB right here, has got to be greater than 12. Smaller than 12, sorry. Because AC has got to be longer than AB because that perpendicular line from a point to the line has to be the shortest distance. All right, let's go through these three theorems here. So if two intersecting lines form a linear pair of congruent angles, then the lines are perpendicular. What I asked my students today was, what's 180 divided by 2? That's 90. So this is 180 because it's a straight line. And then if we know that these two angles are congruent, then we would do 180 divided by 2, and we know that that's 90. Well, if it's a 90-degree angle, both of those angles, then we can say that those two lines are perpendicular. The second one down here, the perpendicular transversal. So on this one, notice we see that the lines are parallel. And we have a right angle here. So if there's a right angle there, there has to be a right angle here because those are corresponding angles. And so that tells us then that all of those angles in there are right angles, and that line Q is perpendicular with line P. On the third one, this is basically just the converse, and it shows us here that if we have two right angles, then the lines must be parallel. Notice that we don't have parallel symbols on the lines R and S right now. And honestly, this is really just the converse of the corresponding angles postulate because there are right angles anywhere there. So we can use that to prove that those two lines are parallel. All right, so we're going to use this now to write a two-column proof. So we were given that R is parallel to S, that angle 1 is congruent to 2, and we're trying to prove that R is perpendicular to T. So here, our first piece of information was given. Now if we go back here and look at 2 and 3 in this, hopefully you see that those are in corresponding positions, so that's going to be our reason. Then I want you to notice that we've got, again, 1 is congruent to 2 here, 2 is congruent to 3. We got the same angle repeated twice, So we can say that 1 is congruent to 3 by the transitive property of congruence. Then we can say that r is perpendicular to t. Again, let's see why. If we're looking at 1 and 3, 1 is congruent to 3. That's a linear pair. Those are a linear pair of angles. And if a linear pair of angles is congruent, then the lines have to be perpendicular. That's what this says. Two intersecting lines form a linear pair of angles, of congruent angles, then the lines have to be perpendicular. All right, let's look at the next one. This one, we're proving properties of lines. So we're going to solve for x first. So we're going to use the same side interior angles because these two angles, hopefully you notice here that these are same side interior angles. And we know that same side interior angles are supplementary. So we're going to add those two together and set them equal to 180. And know again that this angle down here is 90 degrees. So we're going to subtract 90 from both sides. That gives us 2x is equal to 90. And so x is equal to 45. Now we need to solve for y. So we got to figure out how to do that. So let's see what we can do. We could use the linear pair postulate. Notice here again that we have a straight line. So those two angles are going to equal 180. So we could say 3y minus 2x plus 90 equals 180. Put the 45 in for the x. And so that gives us 3y minus 90 equals 90. Sorry, I don't know what this came from, but this should have been 180 right here. And then we're going to add 90 to the other side. That gives us 180. 3y is equal to 180. 3 goes into 180 60 times. Now there's another way to do this. We could use our alternate interior angles. Notice here that this angle should be equal to this angle because those lines are parallel. So we could use that as well. So if we do that, we would say that 3y minus 2x equals 2x. We're going to plug in, again, that 45. And when we do that, we're going to get 3y minus 90 equals 90. We're going to add 90 to both sides. Divide by, again, 3, so we get 60. So no matter which way we do it, we get the same answer. The next one is we're going to write a two-column proof. So what I'd like you guys to do is fill in all the blanks that you can first, and then we'll go back through this problem together. So hopefully you understood that the first step was given. Now the second step, EH is parallel to FG. So it's talking about EH and FG, okay? So I notice that we have this transversal right here, and I also notice that this and this angle are congruent. Hopefully all of y'all can see that by the converse of the alternate interior angles theorem, those lines are parallel. Then, again, we have another piece of given information. So I want you guys to look at the information that's above here. So we have that EH and FG are parallel, and we're given that FG and GH, that's this right here, I have a right angle there. Now, so what can we say? Can't we say that there's a right angle here as well? And we say that because of the perpendicular transversal theorem. So in other words, if the two lines are parallel and one of those lines is perpendicular to then the other one has to be perpendicular. So I'd like you guys to go ahead and work through this proof and come back to me. You guys should really be able to work this whole proof yourself, so we'll see. So the first step is given. Second step was corresponding angles. 3 and 2 are in corresponding positions. Third step was also given. Now again, hopefully you notice, we got 3 and 2 here, 1 and 2. Boom, boom. We're left with 3 is congruent to 1 by the transitive property of congruence. And then we say that r is perpendicular to t because, again, why? Because a linear pair of angles are congruent, the lines are perpendicular. That's what we're looking at, that piece of information right there. You don't have to write all of that, but you do need to say that a linear pair of angles are congruent and the lines are perpendicular. That's what that tells us. On this one, a carpenter square forms a right angle. A carpenter places a square so that one side is parallel to the edge of a board and then draws a line across the other side, along the other side of the square. Then he slides the square to the right and draws a second line. Why should the lines be parallel? Well, let's look right here. So we got this side of the board, and then we've got a line here and a line here. And both of them are right angled from the edge of the board. So if they both are right angle from the edge of the board, then we know that these two lines must be parallel. Both lines are perpendicular to the edge of the board. So if two coplanar lines are perpendicular to the same line, then the two lines are parallel to each other. So the lines must be parallel to each other. All right, let's talk about this last example. A swimmer gets caught in a rip tide. We need to figure out if they should. So in other words, I don't know if y'all know, but this is our shore down here. This is the shore here. And if I'm here, I like swam along and all of a sudden I got to there and I realized, wow, this starts pulling me out this way because that's what a riptide does, pulls you away from the shore. Most of us, our instinct would be to swim towards the shore. Well, the reality is if you do that, then you're probably not going to survive. And the reason is because the current is too strong. So we got to swim out of that riptide. So the key here is what you need to notice is that we want to swim away one way or the other out. So we're either going to swim perpendicular to the riptide or we're going to swim parallel to the shore. That's what we want to look at. We're either going to swim perpendicular or parallel. So let me show you this on a better picture. Again, the shoreline and the path of the swimmer should both be perpendicular to the current, so they should be parallel to each other. So once again, if we're trying to get out of that riptide, then we're going to go parallel to the shore, which is what this line is, or we're going to go perpendicular to the riptide.